This is a picture, or sorry, a composite of pictures of the planet Mercury. We're finally going out, if you were worried that the solar system class is spending too much time around Earth, we're finally going out to talk about the rest of the planets in much more detail. So Mercury, I'm sure you've seen pictures of all the planets in the solar system, and you'll tell me, Professor Cendes, this is not what Mercury looks like. You are correct. This is what we call a false color image. We haven't seen too many of these in this class just yet, but the idea behind a false color image is that the data behind it is real, but we want it to be easier for our eyes to visually see different things in these images. So often if you see an image where it looks like the planetary surface is super enhanced or in a strange color, it's a composite or an enhanced image trying to identify some features. So this is the planet Mercury. I believe this is for elevation. So for example, if you look at the yellow points, you can see that they're corresponding with craters on the surface. It's very pockmarked. So for example, if you want to show where the craters are on Mercury's surface, this is a much easier way to show which ones are the important ones versus just showing a picture of all the gray and trying to dig into what the detail is there. So yeah, we're going to talk a bit about Mercury this week. We're also going to talk about the moon in terms of what the moon is made of and things like that this week. The reason is the moon and Mercury are surprisingly similar in a lot of ways. Your textbook actually treats them in the same chapter. I think it's called Cratered Worlds or something like that. And you guys are going to learn this week why that is. It's a good example of comparative planetology, which we've already talked about in this class. So to begin with, here's a bit of a family portrait of those inner rocky planets. To remind you, so those are the innermost four planets in our solar system: Mercury, Venus, Earth, Mars, and we get the moon as a bonus, our own moon. So if you look at these, I'm sure you guys can see that there's a lot of different things about all these different planets. And I want you guys to think about this a bit in more detail right now. So we're going to spend a few minutes. You and a partner are going to think about some of the key factors if you want to compare these planets. So do comparative planetology. What factors might you observe or measure about these planets in order to compare and contrast them? Let's all aim to have three different things. So it's not easy enough to just say like, oh, they're all different sizes. You have to think a little bit more. Atmosphere, that's definitely a good one. They all had different atmospheres. Yes. That is true. Mars and Earth do have moons. Mars has two moons. They're captured asteroids. So really not the same as our moons, but they do have moons, and Mercury and Venus do not. What did you have to say? Density is an excellent one. Yeah, so what is the density of something compared to water? Something from this side of the class. Anyone want to volunteer? Yeah. Temperature. Yeah, temperature is also very important. I mean, there's a lot of planets that are a lot hotter than other planets. So I just have a few here because I wasn't sure what obviously people were going to say. So the mass, the radius, the composition, what they're made of. All these planets have different compositions. I mean, they're all rocky, we know that, but the percentage of what is also very different. Rotation rate. These planets, as we're going to discuss in the next week or two, all have pretty darn different rotation rates compared to each other. Direction of rotation. They also don't all rotate the same way. They also all have different tilts compared to the plane of the solar system. Interior structure, those can vary quite a bit, as we're going to discuss later today. Things like density of craters. We're going to discuss craters a lot more this week, but we were discussing that, we have a lot fewer craters on our planet because we have a young surface. So that's a good example. That then, of course, implies other places will have way more craters, like our moon. Geological surface features. I mean, there's a lot of different things on our Earth. That happens on other planets. Atmospheric composition, atmosphere mass. So these are all different things that we can discuss. So to discuss planetary evolution, also, where these planets came from, after the planets formed in the solar system, they all formed in the same dusty disk that we discussed earlier, but they then evolved differently. And this was based on a few different things. So things like interactions with different other planetesimals. There's a lot of other stuff that was in that disk at the time. Sometimes you hit other things, sometimes you hit fewer things. Distance from the sun, how close you are to the sun, somewhat depends then on what you ended up becoming. The size of the thing, and the physics, chemistry, and biology, in the case of Earth, maybe others, we'll discuss more later. So, as I said, just as an example of how we're going to be doing this week, the moon and Mercury are very comparable worlds. This is them roughly similar in size and also in true color, unlike the title slide. So, you know, I mean, Mercury is definitely bigger. It is a planet after all, but it does have a lot of craters. It's also a very gray surface. A lot of things are very, very similar between the two. What we can then also see is we can compare these two cratered worlds and think about how do the factors on the left influence the properties on the right. So things like crater density, I listed as a way to compare worlds. You can think of the interior structure, so the thickness of each layer in this planet or this moon, and the atmospheric mass. Do these planets have atmospheres? Or worlds have atmosphere? How much is that atmosphere? So to get going here, we're going to talk about the interior structure of these two worlds, but it's actually going to be a lot nicer if you guys do it first, and then we dig into it more ourselves. So the activity today is you guys are going to think about how the planet's density relates to its material composition, and then describe how the density of these terrestrial planets relates to the size of the metal core inside that planet. So this activity had a final conclusion of a question, which was, which one has the bigger metal core, Mercury or the moon? So will you guys show me what your conclusion was, Mercury or the moon? Okay, Mercury has it, and that is a good news because it's actually correct. Yay. So let's talk about Mercury a bit. So as a quick overview of the planet Mercury, this is what it looks like when you don't have a cool false color image of the planet. It is the closest planet to our sun, and it is so called Mercury because that's the winged messenger of the gods in Roman mythology. It is one of the planets that we've known of since antiquity. And the thing about Mercury is it's called, you know, the winged messenger of the god because it does not really stray from the sun. As you can imagine, it's orbiting the sun much, much closer than we are. And as a result, what that means is it doesn't go more than 20 degrees or so from the sun at any given time. As a result, it's really tough to spot Mercury unless you really know what you're doing. To give you an idea, Mercury is actually right now at one of its greatest distances this year from the sun. And 2 days from now, it's going to be all of 8 degrees from the sun. So if you got a really good horizon, you know, maybe you will go to the top of Skinner Butte or something. I looked it up for you. 6:08 Mercury, or the sun sets, 6:56 Mercury sets. It's only going to be about 8 degrees from the sun. As a rule of thumb, if you hold your three middle fingers out like this is about 5 degrees. So really, really close to that horizon. It's going to be a really bright sky, but if you really know what you're doing, you'll be like, oh, there's a dot there. So winged messenger of the gods, you can imagine there's this one planet that's barely showing up and then disappearing again. Like I've seen Mercury a handful of times, but it's usually because it's like an unusually good time to spot it in the year or something unusual. So then sometimes you manage to spot it if you're lucky. What we really know about Mercury, though, is thanks to various missions that have visited it through the years. Not too many compared to some places that we're going to talk about, like Mars. The first time it had a flyby. So flyby is when you don't actually go into orbit around a planet. That's much, much more complicated dynamically. But Mariner 10 did several of these flybys in 1973 to 1975, just like kind of as it's going around the sun. Sometimes it got close enough to take some pictures. Did not actually even take enough pictures to cover the full surface of the planet. Just to give you an idea, though, that flybys, you know, they're less ideal, but they're much cheaper to be able to do. But then what happened then, we didn't really go to visit Mercury for many, many years. And then Messenger was a messenger. I looked it up. Messenger is short for Mercury Surface Space Environment Geochemistry and Ranging. Astronomers really, really like to have acronyms in our names for pretty much everything. So most of our detailed information about Mercury is from the Messenger probe, like that picture I showed you guys at the beginning of the lecture. This is also a Messenger photo. But it's worth noting that next year, Bepi Colombo, which is a combination mission from the European Space Agency and the Japanese Space Agency, is going to go into orbit around Mercury next year. So we're going to learn a lot more about Mercury in the next couple years beyond what we already know. So composition and crust. It is about 60% metal by mass. and has a solid mantle and crust with an iron nickel core. It actually does have, this is fun, a weak magnetic field. By weak, I mean about 1% that of Earth. So like you're not going to use your compass to figure out how to travel on the surface of Mercury. So what this tells us then, this is a question for you guys. If we know that Mercury has a magnetic field, the core of Mercury must be one of these options. And which one is it with your A, B, C, D cards? Okay. The answer is 2 or B. The fact that it has a magnetic field, we discussed last week that we have a magnetic field on Earth due to the fact that we have a liquid core that creates a dynamo. So what this tells us is that on Mercury, we do actually have some sort of liquid core if there's still a magnetic field. So this is actually very surprising in planetary evolution. We don't actually fully understand why Mercury has a magnetic field. It's thought to, like, until they detected one, they thought, oh, it's impossible, it's too small for that to exist. And it does. So, you know, this is one of those things where nature always has, you have your best ideas and nature has better ones. So if we're thinking about things, so which criteria might influence interior structure? 2 of these options are correct. The first is you could have some sort of interaction with other planetesimals. And you could also have something to do with the size. So, you know, we were discussing how you can get these different layers and strata depending on, because of the Earth size, it differentiated. Differentiation also just somewhat depends on the size of the thing. You can't have too many layers if your planet is not big enough to have them. Distance from the sun actually doesn't matter too much for something like this, for the interior structure. I mean, the sun does affect things like our atmosphere, things like that, but it doesn't affect the structure of the planet as much. And the physics, chemistry, biology is less important compared to these things. So key characteristics of the planet Mercury. It is not that massive. So it is, you know, about 5% the mass of Earth. It's about 1/3 the size of Earth. This has to do with volume. As you get bigger, you get a lot more mass. The density is actually not very high. It has an orbital period only 88 days. So it goes around the sun fairly quickly. I mean, compared to our 365, that's probably not surprising. Rotation period, though, days are much, much longer. And as far as we can tell, it does not really have any orbital tilts. So we discussed how we're about 23 degrees from the ecliptic. Mercury is pretty much straight up. So I want to discuss these 2 because this is actually gives us a really interesting thing that happens in Mercury's orbit. The fact that the orbital period and the rotation period of the planet are so pretty comparable, honestly. So I also want to point out that despite its large core, Mercury is actually less dense than the Earth. And this has to do with the fact that the Earth is bigger, so it's been able to compress more, basically, in its size. So Mercury completes 3 spins for every 2 orbits. So it spins every 59 days. Its orbit is 88 days. So this ends up happening because of something called orbital resonance. It has to do with it's so close to the sun that it's gravitationally interacting a little bit more with the sun. It changes its velocity a bit, so the days are really in sync with the sun. So if I have this little simulation, which I am about to show you guys here. So we're going to, you know, have Mercury, and you're standing on Mercury. We're going to have it. Take a look at this day-night here. So what ends up happening due to the rotation of Mercury is as the sun is going, you will basically have the sun pause and stand still in the sky if you were standing on Mercury. And this has to do with the fact that because that orbit takes, it's going again, see, so you can watch, it's going to pause. It actually even goes back a little and then keeps going. And this is just because the day on Mercury takes so long that if you were to track the sun, the day is actually a very long time and it would be very, very confusing. You can't really use the sun to set your watch on Mercury is the way to think of it. Mercury also has extreme temperature swings. So the surface will swing from highs of about 430 degrees Celsius to lows of about minus 180 degrees Celsius As a reminder, you boil water at 100 degrees Celsius. So it gets plenty hot and it gets plenty cold on the surface of Mercury. However, despite that, one of the interesting things that Messenger discovered when it was studying Mercury about a decade ago is it did detect water ice within permanently shadowed craters. So this happens on the moon as well. We're going to discuss it, I think, more on Wednesday. But the general idea here is imagine you have a comet that has a lot of water ice on it. It hits the surface of Mercury, has impact, and is going to be permanently in shadow. So at minus 180 degrees Celsius, it's going to sit there as ice for, the rest of time until something actually finally hits it and vaporizes that ice. So I guess if you wanted to live on Mercury, that would be a little bit easier for you because there is actually water ice down there. Atmosphere. So here's a question that I'm going to put to you guys, which is which of these different criteria might influence atmospheric mass for a planet? So how much atmosphere it has. There's actually 2 correct answers, so you can choose which one you think and show me that. Okay, so I saw mainly B's and C's. Yeah, I guess D is maybe a little too open-ended. I might change that going forward because everything you don't understand can just be physics, chemistry, biology eventually. But the ones that really matter are the distance from the sun, because those solar particles that we were discussing last week can really affect your atmosphere. And the second is the size, for reasons that we're about to go into, which have to do with something called escape velocity. So escape velocity is the minimum speed you need for an object to escape a planet's gravitational pull. So if you want to launch a rocket and you want to go into orbit, you have to reach a certain speed in order to be able to leave the surface of the Earth, right? Makes sense. It is defined as the escape velocity, V subscript S, equals, in kilometers per second, 11.2 is the constant factor in front, but it's the proportion is the square root of the mass of the body relative to the size of Earth. Remember, Earth is 1, divided by the radius of that body, once again, relative to Earth. So now that we have this equation, and I'm going to show it to you guys here, I'm going to ask you, do you think gases are more likely to escape from less massive planets or more massive planets? Okay, so I saw some confusion. So less massive planets. So imagine here, for example, the radius of the planet is the same. We're not going to change that one. Mass of the body, let's say it's just 1, so it's the exact amount of Earth. Now imagine you had a planet that was 10 instead of 1. You put that into this equation. What you're going to get is a escape velocity that's much higher. It is much harder if you were on the planet, if you were on Jupiter, if Jupiter had a surface, trying to leave the surface of Jupiter would be much harder than leaving the surface of the Earth, just to give you an example. Temperature and speed also matter for how this works. So I have a little simulator here to show you guys what exactly this means in terms of the average of a gas property. So let's see where this is. So we have a simulation. We're going to explore. And what we're going to do is we are going to release a ton of particles into this system. So you can see they're bouncing around. It's at 300 Kelvin, which is the equivalent of 27 degrees Celsius. I'll put it there for reference. And you can see that they have a certain speed, right? So what we're going to do now is we're going to make it colder. Notice that temperature is really, really dropping. We're going to give it a couple seconds to drop further and further and further. And you can see that those molecules or atoms or whatever they are, particles, have slowed down quite considerably compared to when we first had temperatures that were 200 degrees hotter. Basically, you need some temperature in thermodynamics to have these particles interact with each other, is what this means. And yeah, when you get down, this is basically right above absolute 0. Particles are barely moving. So if you have the escape velocity for a certain gas, the average speed is 0.157 value in kilometers per second. the square root of gas temperature in kelvins. So Kelvin is a temperature scale where 0 is absolute 0. So that is, you can't have temperatures go lower than that. Basically, atoms like would break apart and fall apart. I guess nobody actually knows, but that's the idea. If you were to hit absolute 0, 273 degrees Kelvin is the equivalent of the 0 degrees Celsius, divided by the molecular mass relative to hydrogen. So how many molecules or how many protons you have in something. So hydrogen is 1, is what we mean by this relation. So with this, if gases are more likely to escape from, do you think it's cooler planets, warmer planets, or planetary temperature doesn't matter? And here's that equation for you again. All right, I'm seeing only B's. So yes, you guys are correct. Warmer planets are what would have gas escape faster. So this means distance from the sun does matter. As I said, you know, gets much hotter if you get really, really close to the sun, much cooler the further out you are. So atmospheric composition then of a planet depends on the escape velocity, which depends on the planet mass, and it depends on the average velocity of the molecules, which depends on the temperature. So 2 different factors. Why do I say the average speed? So you might have noticed in that simulation earlier that not all the molecules were going equally fast. Speeds are going to vary in a distribution of different speeds in a certain sample of molecules. And that means that you're going to have an average molecular speed in any given system. You can take a lot of complicated classes in this physics department if you really want to know the details of how this works. But as a general rule of thumb, if a gas velocity exceeds about 1/6 of the escape speed, the fastest molecules in the bunch will slowly leak out of that atmosphere over about 4.6 billion years. It can definitely be shorter than that. I'm just saying 4.6 billion years because that's the age of the solar system. So this just roughly means, are you still going to have an atmosphere today or not? Is what we're really just trying to answer because we are observing all these planets today. This also means that if you have an average speed that's 6 times the escape velocity, you're not going to find gas in that atmosphere. You're basically going to have an atmosphere that's been completely stripped away over time by the temperatures there and the size of the planet. So with this, I'm giving you the average speed on Mercury, and I'm giving you the escape velocity on Mercury. Do you expect to see nitrogen on Mercury today? So the gas nitrogen, which I told you guys last lecture, is about 70% of the atmosphere in ours. And the real question you want to ask yourself, multiply by 6. Are we going to see nitrogen? Are we not going to see nitrogen? Yep, so 6, it's going to be 4.8 versus 6. So you are going to have a greater escape velocity. So yeah, you're not going to have any nitrogen on Mercury because you have 4.8 kilometers per second, which is greater than 4.2 kilometers per second, which is the escape velocity for Mercury. We're going to do this for other planets going forward. So if you're not sure, just a reminder, I also have the recordings of these and everything like that on the Canvas website, so you can revisit this. So Mercury has no atmosphere. It has a very low mass, and it has a very high temperature that's due to being very close to the sun. So it has all been stripped away. There is some gas. It has what's called an exosphere, which is a very, very, very thin layer of gas, like better than most vacuums you could get in a laboratory on Earth levels of thin. And it's basically created by those solar wind particles that are streaming, you know, a lot more of them stream past Mercury due to being closer to the sun than they do to the Earth, and very small rock collisions over time. So it's mainly sodium and oxygen. And just to give you an idea, our Earth atmosphere pressure is defined as 1 atmosphere. Mercury exosphere pressure is about 10 to the minus 14 atmosphere. So it's, for the human purpose of us humans, it's as much as it's the equivalent basically of being out in space, more or less. The moon, I'm just going to tell you guys right now, is going to also not have an atmosphere. And its pressure is even less than that of Mercury. So This is a world that is, you know, very cratery. It does have a magnetic field, but that magnetic field is not really doing too much for it. Does not really have an atmosphere and has a very unusual residence in its orbit compared to what we have for, say, our planet. So just to wrap up, what we're kind of discussing today, what we're going to be discussing going forward. So the interior structure, these are kind of goals. So like what you should be able to do for this class if you're thinking ahead to the final. So if you think of the moon and Mercury's interior, you should be able to explain how they're different. And atmosphere mass, explain what factors cause planets to retain or not retain an atmosphere.